Inverse of parent quadratic function. Now in these set of videos we will try to understand how to find inverse of quadratic function in different ways. Now this is the very first one where we will discuss the parent function and then we will discuss about transformed quadratic functions. Now here the question is A. Graph the function f of x equals to x squared and its inverse. B. State domain and range of f of x and its inverse. C. Determine whether the inverse of f of x is also a function. And D is, how can you restrict f of x to ensure that its inverse is a function? Now I've already given you the graph of fx equals to x squared, but let's go through it once. So to draw the graph of fx equals to x squared, we can take some critical points, which we call the key points for the function, parent function x squared. So these are, let's take x and y values as x equals to -2, -1, 0, 1 and 2. So the function is y equals to x squared, right? So y is actually equals to x squared. So we'll square these and write down as the y values. Square of -2 is 4 plus 1, 0, 1 and 4. So we get these coordinate points, right? So the coordinate points which we get are -2, 4, -1, 1, 0, 0, and then we get again 1, 1 and 2, 4, right? So these are few points which will help us to sketch the quadratic function fx equals to x squared. So this is 0, 0, then we have 1, 1 and then 2, 4. Similarly, on the minus side we have our points, correct? We can extend it. We can also have 3 square is 9, and on this side -3 square is also plus 9. So as you see, in this particular function we have even symmetry. So whether the x value is plus or minus, the y value is always positive. Now to find the inverse, one method is that we can swap these points. That means we have a point starting from, let us say, take the first 5 points which I have considered. So if you swap, that means -2, 4. If I write this as 4 minus 2, I get my inverse function points. Do you get the point? So what we will do is, to find the inverse function, we interchange these values. We write x here and y there. That is what really the inverse function is. So inverse function is, we get the inverse of the function by swapping the points. So if the function for us gives us the coordinate points x and y, then the inverse will give us the points y and x, correct? So that is how we get the points of the inverse function. So let's plot the inverse of these points. So first one will be 4 minus 2. So we'll take this as the x value and that as the y value. 4 minus 2. So 4 and -2 will give us this point. And then we have 1 minus 1. So 1 minus 1 is that point. 0, 0. 0, 0 is this point. So what we really did was, we took these points from the negative side. That means we took these points, and with the result we got them, right? So if we also take -3 and 9, which is kind of here, then we'll get 9 and 3, right? So 9 and 3 minus 3 will be this point for us, correct? So if I connect these, I get inverse of left half of my parabola. So let me connect them and show you the left half of the parabola. So it is like this, correct? Now the right half of the parabola, I will show you a different technique to find the inverse, and that is by reflecting it on a line y equals to x. So here we have a line y equals to x. If I reflect my graph on this line, I get inverse of that. So let's do reflection. Now this point remains here itself, 0, 0. Since it crosses y equals to x, it is common between our graph y equals to x squared and the line y equals to x. Now 1, 1 is also on the same line. So these points are called invariant. They will not vary. They will remain there itself. Now, let's consider the next point, which is 4. If I am treating this as a mirror and reflecting it, so reflection will be 1 unit diagonal will give me that point. So that is the reflection of 0.24, which is actually 4.2, right? It is same as we did earlier. Now let's look into the point 3 and 9. So 3 and 9 is right there. Now to reflect it, we go diagonally 1, 2, 3 units. So it goes, the mirror image will be 3 units on this side. 1, 2, 3. So that is the point of our interest. Now if we join these points, we get our graph, and that is this. So do you see? So we have inverse of our function where this top line reflects the right arm of our parabola over the line y equals to x. Now we could have got the other half also by the same technique of reflection. Let's check it out, right? So let me show you how it matches. Let's start with this point. So we go 1, 2, 3 units. So 1, 2, 3 units, you get the point. Do you see that? So that is how we can reflect each point and get inverse by reflecting the graph over y equals to x. So by this, I've shown you 2 techniques how to find inverse from a function. One is you can mark some points and swap them. Second is reflect your graph over the line y equals to x. So that is how you find inverse of any function for that matter. Okay, now part B is to find domain and range of f of x and its inverse. Now, domain of our function x square is all real numbers. So let me write down domain here. So x belongs to real numbers is the domain of our function y equals to x square. And the range is, the domain is x belongs, so domain of our function is x belongs to real numbers. And the range is y belongs to real numbers where y is greater than or equal to 0. Now if you see the graph, you can clearly see that the domain of your inverse function, that is f inverse, is really x is greater than or equal to 0. So x belongs to real numbers, but x is restricted. It is only greater than or equal to 0. As far as range is concerned, you'll find that y belongs to real numbers is the range, since y can have any value. So what has happened here, that in the inverse function, they have swapped. Now x belongs to real number was the domain. Now that becomes the range. Do you see that? And the range was y belongs to real number, but y greater than or equal to 0. But here it has changed to domain. So when we swap to get inverse of a function, their domain and range also swaps. Correct? Third part is determine whether the inverse of f of x is also a function. Now we have inverse here, which has 2 parts, right? If I draw a vertical line, it intersects at 2 points. Since it fails vertical line test, we know it is not a function. So what we find here is that f inverse is not a function, since it fails vertical line test. Now part D is how can you restrict f of x to ensure that its inverse is a function. So one way to restrict is to restrict the domain of your function. So let us say if we consider only 1/2 of our parabola, that is if we consider only the right side, that is if we say x is greater than or equal to 0, then we are considering only the right side of our parabola. Its inverse will be the one given on the top. Now since we have only half of it, it will pass the vertical line test and thereby it will be a function, right? So that is a way to restrict. So the restriction is that we could restrict x as greater than or equal to 0. In that case, inverse will be a function. Alternately, we could have also restricted our domain to x less than or equal to 0. Then we would have got this as our function and the lower half as the inverse. So both options can work. But the important thing is, either side of vertex can be taken, right? So you could take either greater than or less than the vertex value or the axis of symmetry, right? Then it will pass, the inverse will pass a vertical line test. Let me add here, if in the function you draw a horizontal line and it crosses at 2 points, then its inverse will fail vertical line test. So even when you look at the function, you can make out whether its inverse will be a function or not by drawing a horizontal line, and we call that as a horizontal line test. I hope this video helped you to get all the things together. And now we will have test problem for you, where we will have transformed quadratic function and you need to sketch it using either the method of swapping the coordinate points or reflecting it on the line y equals to x. I hope you appreciate it. Thank you and all the best.